Hi guys, I'm trying to pair program with my friend, Jason, who is not here, but I'll try to pair program with him. Okay, so Jason, let me start the timer. Okay. All nodes distance k in binary tree. Okay, let's listen to this problem by Google Translate. Oh, not this. Because in real interview, you need to listen.
Given the root of a binary tree, the value of a target node target, and an integer k, return an array of the values of all nodes that have a distance k from the target node. You can return the Given the root of a binary tree, the value of a target node target, and an integer k, return an array of the values of all nodes that have a distance k from the target node. You can return the answer in any order.
Why is she so slow? So it says distance. So what's the meaning of the distance? So for example, in this case, we need to know the meaning of the distance. What's the name of the meaning of the distance? Here k target 5. From the target node. So 5 to 7, and then 5 to 4, and then 5, 3, 1. So these are 2, right? And then if in case of 2 and k is 3, then 1, 2, 3. 1 is also the answer. Okay. So going to the bottom, going to the child is very straightforward. But going to the top is not very straightforward. So and then one thing is that we don't know where 5 is. So first of all, we have to find 5. And then we have to calculate. So 2 actually, 5 depth is actually 1. So from 5 to the 2, k is 2 actually means that we can go to the depth 3 from 5. Because depth of 5 is depth 1. And likewise, if we go up, okay, so in this depth, so we know the depth of each node, right? So if let's say some case like here and here and here and here like this. So here like this, and then you think that if this is the node and the 1, 2, 3, and k is 3, for example, In that case, we know that this is 1 and this is 2. Oh, we found that. And then what it means that some nodes are here, then somehow oops, yeah, 3, K3, then what we need to do is that 1, 2, 3, 1, 2, 3. So how can I my feeling is like BFS is better. Can I why does it always show the palette? Oh, it's not. So in BFS, breadth first search, we add this and then we add this, and this will be popped out. So we don't know whether this blue node is in here, under here, or under here, right? So then from here, we now know that, oh, blue node is here. And then if K is 2, we have to return this one. But this node, there's no information left, right? If K is 3, we can return this by looking at the sibling. But another case is that if this is left side, then we already lost. So the question is how to go up. How to go up? One way of doing that is to store the information before this into somewhere. There is one way. Or we can revisit. So we found this node. And by doing depth first search, oh, we found this. And then since depth first search is using recursive, we know that this and this so with DFS, if we found that node, then what can we do? Then we can go up and we can go down. And going down can be done by calling DFS. But going up, we have to return something. So let's say that going up, return like, for example, like 3, and then this guy minus it 2, and then in this case this guy needs to find node with 3 under here, node with 2 under here, so this will be the answer. And then node 2, they return 1, so this guy will find 1 from here, so this will be returned. So here's how it works. With DFS, find the target. Start from the target, call, not call. Call. Find the nodes. This one is easy. Yeah, so interesting thing is, when we know this guy, when this will return, for example, -1, I am not, meaning I am not the target. This guy knows that, oh, this guy is target because it returns 2, returns 3, and this guy try to find 2 under is 2 here, and then this guy return 1, and this guy try to find distance of 1. Oh yeah. Not sure still, but let's try to write int dfs. So int test okay. So what I can do is that if cannot know the null pointer unique number of nodes is more than if node.val equals target, then I am the target. And then vector v so here's what I think. So if node val is target, then what should we do? Then we can call dfs node left. But here we don't need to find the target. And then now we need to find k minus 1. Is k can be 0? Jason, yeah, k can be 0. So if, yeah, so here, if k 0, then what it can do is they can add pushback. Node. DFS. And we also need to go through the right. Yeah, things like that. So this way it will go to here, and then it will decrease the, and then else, not target. So basically, interesting thing with this is that are we looking for a target, and are we in the middle? Did we find the target? So this code is like, did we find the target? And else, so we need to have some kind of flag. I set it to null when we have find the target. So if target is null pointer, null pointer, have found the target. So this is the code for the I have found the target. So the reason why it is called is that because this is child, right? Called by child of target. Predecessor target by here. So here, if k is 0, we'll do this. Otherwise, we'll do this. So here now target is not null, which means that we haven't find the target. So so in the case, when we found the target, then we start to do this and return k. But here, one thing we need to check is that if k is 0, then what we need to do is v dot push back node value and return. What should we return? So here I want you to return something, meaning that let's think about this later. So let's think about this. If we found the target, already found the target, then do this, and this is way more complicated. What if we store these values somewhere? If this node that its parents is this one and its sibling is this one, this is not well balanced binary tree. this is just a binary tree, right? So there might not be this one, right? So oh, so once we found this, K3. So we need to go this way too. And then we need to go this way too. So let's think about, let's stick to this solution, but let's think about precisely about each state. So we have some context like ball found, right? So initially this is false, and then if found, and then if not found. So when is found? When is not found? In case of its ancestor, it is always not found states. Called by, yeah, and then this is called by. Yeah, so I think this is it. And when it's not found, what you're gonna do is that not found actually means, well, I am a target or ancestor or sibling, right? So in this case, result, we can check the result, then if result is this one, so -1, this will go, so this will actually return -1, I'm not, I don't know what target is, -1, and this guy, oh, not -1, and this guy calls this, from here -1 is not important, but for this guy, so So here, if k is, so if there is only one node and the k is 0, then this node must be returned. So here, when you call here, not found, oh here, okay, and then push back and then return, done. So it will return. When a value is 1, then when a value is 2, then this guy returns 2, because excluding self. So this here it will get 2, right? So if the value is more than this one, the node should do something. The parent should do something by calling, since this is left, we'll call DFS the right side. So this returns 2. Here we'll pass 1 above 0, right? So rest minus 1. And getting rest actually means the found is true, so they will be somewhere in here, right? And then it will return rest minus 1. And here you also need to do this. So for example, if it's 1, 0 will be returned, so you need to add itself. Return. Likewise, I don't know. This does not look correct. 24. node cannot be null, but target can be null because we return null pointer. And I am doing, if target is same, found is here, meaning the target is null. Target. Member access within null pointer still. So here, not found. So we go to here, and then we do this, and we do this. So it goes to the left first. So here. So still not found. So we go to left again with here. So now you're here. And then now, and then next turn, this will be called. And here, still not this. And then there's nothing. So we just return -1. And from here, this returns -1. This returns -1. So returns -1 too. And here, this is -1. So it goes here. Then it has the right side. So it goes to the right side. And what should I do with K? So from here, not found. Oh, but now these are same. And then K is not -1. K is, so it goes to this direction. So now it's found. So anyway, it returns K -1, this one. So here, so in its code, now K is 2. So node right, so this returns 2. So it goes to the left. And then with 1 value. So now I found, and then case 1, so go to here. I guess this works. Still runtime exception. Assert node. Assert target. Target is no. Target is no. Not found, but target is no. This means found. Target should not be no. So when do we set the target? Here, but it's found. And then here, oh, like this. Okay. Oh, wrong answer. So this is 1, 0, and then 1, then no. Then 3, 2. Then 3, 2. What? 2. Like this. So 2k is 1. So we have to return this, right? So -1, -1, -1, and then still not found. So this one actually calls here, right? And then in the code for this one, now its value is same. So found is true, and k is currently 1. Then there's no child, so it returns 0. So this returns 0 actually, yeah. So which means that we need to do something like this here. So 0 is returned. Oh. When 0 is returned, it means that I hate this code. I hate this code. Even though it might work. Wrong answer, still. Okay, let's give up. I spent like 43 minutes trying to solve this. Maybe my whole approach is wrong. Instead of instead of doing go back up, I need a better way to find the ancestor. Where is this mark? Tempted. What would be the best way to find it? Go up to the ancestor. let's say that this is target and then we have 2. And then let's say that there are some more node underneath here. And then if we don't want to mess up with this structure because okay, let's see how other people does. Java solution, BFS, DFS, BFS, convert to graph, then level order traversal. Yeah, this is one thing I was thinking. For example, because that's why I told you, like, we must not modify the input, but rather than saying that, I may be better to I'd better to ask you whether instructor. So the way I was thinking is that yeah, that is also not very easy. They are so great, so much great guys using hash map. Hash map. With this hash map actually might map by giving 2, it will giving 1. By giving 1, it might give 0. So it might contain some way to go up. Oh, this is long. So what this guy does is that ABC distance K, it first does ABC. What ABC does that it has map, unordered map, oh, name is parent. Okay, so parent left is parent, so it creates a hash map, and then after that it has Q, and also it has visited a lot of new structures. And then while it is empty, count is K. What's K? Count. Break. Q1. What's Q1? Q. I don't know why this guy does push and pop things. Maybe there's a reason. Let's find a better one. Sorted by most vote. Without using but we know if the distance from node to target is k, the distance from its child to its target k plus 1. Store the value distance in hash map from all node in the path to target. Distance from a node to target node. A node to target node. Distance from its child to the target node is careful. Unless if child node is closer to the target node, which means that target node is in a subtree. So we need to traverse the tree first to find the path from root to target. To find this root, store the value of distance in hash map from all node in the path to target. Then you can easily use DFS to traverse the whole tree. Each time when you meet a tree node which has already been stored in the map, use the stored value in hash map instead of distance k, find target. This map. So inside find, with this, the map put root this. Left find, right find, and then return. Left find. If left is larger, then root left. Oh, this is the return value. -1. say it's 1, k is 1. So find, so here, find right and target. So inside here, it's found. So it returns 0. So this right is 0. So it put 1 and then it returns 1. So in case of 0, it's left. So this guy will put 2. So inside the map, this one for 2, this one for 1, this one for 0. Right? And then DFS, root target, get map root. This one's, what's the third one? Root target k and then length. So if k is 1, then this length is minus 1. No, 2, right? And the last element, result, is and then if the map contains root, then it gets the root. Node. If length is 1, then this will, we'll consider the length is 2. So this one is 2, we'll add this. And then root left, root right. So this one will be called with DFS. And this one is in the map, so length 1. And now this is not true. And then I will do left and right with this was 1, right? Now it calls with 2. 2. So DFS left, because it's 2, it's been added. And how about this one here? So length is now 0. So this is not match. Then this calls length 1. Code is short but hard to understand because of this length. Length sometimes is passed and length sometimes get from the map. But the interesting thing is that it stores this by finding the target for the first pass, and then from that if k is 2, then this know that, oh, I am the value, and this guy does not know whether k2 now is k1. K1 you need to go this way or you need to go this way. So you need to, if we go this way, and now k is 0, but so it can be added, and here now k is 0, but it's target. So in that case it will be yeah. If k is 3, and if we have some more node in here, this guy is 2, and we need to find 3, k3. So this guy will try this way or this way. So this way is not the ancestor of 2, so it will be selected. And this way is ancestor. So okay, let's ignore the information you gave me. Let's start with the k value that I have. So let's start from which is 1. So this guy tried to, try to go here and go here. Oh, this problem is very complex. Vote was voted. Python, easy to understand. Using recursion to find all the son parents pair into a map. And GFS to find the k distance node. So distance k, find the parents. Okay, GFS. Shift